Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Somewhere out there, right? Like deep in the dustiest, absolutely most violent center of our galaxy, there is this invisible cosmic metronome that's just been ticking away for over 30 years.
Yeah, it's pretty wild to think about.
Right. Just imagine the sheer scale of that for a second. Every 20 minutes, just boom, a massive blast of radio energy washes over the Earth. It's perfectly timed, it's incredibly powerful, and it is utterly invisible to the naked eye.
Completely invisible, yeah.
And for decades, the absolute smartest astrophysicists in the world had absolutely no idea what was setting off this timer.
None at all. It really is one of the most, eerie pictures in modern astronomy. You have these phenomenal bursts of energy just rhythmically pulsing out of the absolute dark.
Like clockwork.
Exactly. And we're picking up the signal. We know something enormous is out there generating it, but the actual mechanism behind it has just remained this complete void in our understanding.
Well, our mission today is to finally unravel that exact mystery. We're going to explore what astronomers call long-period transients, or LPTs.
Right.
And we're going to look at this truly groundbreaking new discovery. It's a specific star system designated A-Scopo J1745.
Yeah, quite a catchy name, right?
Oh, they always have the best names in astronomy. But this single, newly mapped system is finally giving the scientific community the answers they've been so desperately searching for.
It's changing everything, honestly.
Okay, let's unpack this. Because to understand why this new discovery is so revolutionary, we first have to look at how these signals behave in the wild, right? Like, why are they so incredibly difficult to track down in the first place?
So when we talk about a transient in astronomy, we are generally talking about, anything in the sky that changes over a short human timescale.
Short meaning what, exactly?
Like a star exploding, a comet passing by, maybe a solar flare, just something that happens relatively quickly. But a long-period transient in this specific context refers to objects that produce these bright, repeating bursts of light, specifically at radio wavelengths.
Okay, got it.
Now, the universe is it's a noisy, flashy place. We are actually quite used to things bursting in space.
Right. Things blow up all the time.
Exactly.
Right.
But the timing of these specific LPTs is what makes them such an absolute anomaly. Usually when we find fast-flashing objects, they repeat very rapidly.
Like how rapid?
We're talking fractions of a second. But these objects, they operate on a completely different, almost languid time scale. They repeat on the order of minutes or sometimes even hours.
Which, if you think about the sheer amount of energy required to send a signal across the entire galaxy, a 20-minute gap feels like an eternity.
Oh, it is an absolute eternity in high-energy physics. And their behavior is wildly inconsistent, too.
Inconsistent how?
Well, as you mentioned at the beginning, we have some of these LPTs that have been pulsing with this perfect unbroken rhythm for over 3 decades.
Just nonstop.
Relentless.
Yeah.
A totally reliable beat. But then you have other transients in this exact same category that will pulse rhythmically for a while and then just, go completely dark for days at a time.
Just nothing. No signal at all.
Nothing. And some go permanently radio silent. It's as if the engine just flooded and shut down forever.
And that's frustrating. And to make matters even more complicated, almost all of these LPTs have been discovered right in the middle of the Milky Way, right? Like close to the galactic center, which is essentially a massive cosmic smog bank.
That is honestly the perfect way to describe it. It's a smog bank. The center of our galaxy is just packed with these dense clouds of gas, interstellar dust, carbon, silicates, ice.
So it's just filthy out there.
It really is. And this presents a massive observational hurdle for us. You can't just point a standard optical telescope like the kind that detects visible light at the galactic center and expect to see what's going on.
Because the dust acts like a physical wall to the light, right?
Precisely. It comes down to how different wavelengths of light interact with physical matter. Visible light has a relatively short wavelength.
Right.
So when it hits a microscopic particle of cosmic dust, the light wave just scatters. It bounces off in a completely different direction and never actually reaches our telescopes.
Which is why the center of the galaxy just looks dark to the naked eye.
Exactly. But radio waves, they have incredibly long wavelengths. We're talking meters or even kilometers long.
Oh, really?
Oh, yeah. So instead of hitting those tiny dust particles and scattering, the radio waves just glide right over them. They pass completely through the galactic smog and eventually hit our radio dishes here on Earth.
Okay, so I am imagining this like trying to observe a street scene while standing on the roof of a skyscraper in a heavily smoggy city.
Okay, I like that.
Right, so you are looking down, but you cannot see a single car, a single pedestrian, or even the street itself because the smog is completely opaque.
Right, it's just a wall of gray.
Exactly. But every 20 minutes, you hear this massive, booming car horn cutting right through the air. You know for a fact something huge is down there making that noise, but you have zero visual confirmation of its shape, its color, or like how many wheels it has.
What a fantastic visualization. That is exactly the dilemma. You only have the sound of the horn, which is our radio burst. Because you can't see the actual source, and because these bursts happen so infrequently, they're remarkably hard to discover.
I'd imagine.
Most radio telescope surveys, they scan the sky very quickly. They look at a patch of sky, record what's there for maybe 5 minutes, and then move on to the next patch.
Oh, I see the problem. If you are only looking for 5 minutes and the object only pulses every 20 minutes.
You're going to miss it almost every single time.
Wow. Which explains why we know of a few of them.
Exactly. Despite the vastness of the galactic center, astronomers have only managed to catalog about a dozen of these strange sources to date. Just 12.
That is a tiny number for an entire galaxy.
It really is.
Yeah.
And what's fascinating here is the sheer diversity among just those 12 objects. I mean, even within such a tiny sample size, their pulse profiles, their brightness, their periods of silence, they're all completely different.
They don't match.
Not at all. They don't neatly fit into a single, easily identifiable category.
So if you are an astronomer and all you have is the booming horn and the smog, how do you even begin to guess what's making the noise? I mean, you have to look at the vehicles you already know about, right?
You start with the usual suspects, yeah. When you only have repeating radio pulses to go on, you have to ask the fundamental question. What else in the universe produces repeating radio bursts?
Okay, and what does?
Well, for decades, the absolute undisputed king of the repeating radio burst has been the pulsar. So the initial rating theory, the assumption that drove a lot of the early research, was that these LPTs were simply pulsars that were just spinning very, very slowly.
Okay, let's look at the pulsar theory, because my understanding is that pulsars are some of the most extreme objects in existence. Like, they aren't normal stars.
Oh, far from it. A pulsar is a highly magnetized rotating neutron star.
And a neutron star is...
Well, to understand what that means, we have to look at how a massive star dies. When a star much, much larger than our sun burns through all its nuclear fuel, it can no longer support its own weight against the crushing force of gravity.
So it collapses.
Violently. The core collapses inward in a fraction of a second, and the outer layers are just blown away in a massive supernova explosion.
And what's left behind in the absolute center of that explosion is the neutron star.
Yes, and it is dense. You take a mass roughly equivalent to our entire sun, and you crush it down into a sphere about the size of a small city.
Right, like a city like 20 kilometers across.
Exactly. The density is just incomprehensible to the human brain.
Yeah.
A single teaspoon of neutron star material would weigh billions of tons.
That's insane.
And because of the conservation of angular momentum, much like an ice skater pulling their arms in to spin faster.
Right, they pull their arms in and suddenly they're a blur.
Yes, exactly. Because this massive core collapsed down so drastically, this tiny, ultra-dense sphere is rotating at staggering speeds.
And that rotation is what creates the lighthouse effect we see from Earth. Really.
Right. These neutron stars have intensely powerful magnetic fields. As they spin, they funnel charged particles to their magnetic poles, accelerating them to near the speed of light and blasting out twin beams of radio waves.
So it's shooting out beams from the top and bottom.
Essentially, yeah. And if the star's magnetic axis is tilted relative to its actual rotation, those beams sweep through space like the beam of a lighthouse.
Oh, I follow.
So every time that beam sweeps across the Earth, a radio telescope picks up a pulse. That is your pulsar.
Okay, but here is where I see the physical contradiction with the theory. You mentioned that an ice skater pulls their arms in to spin faster. Yeah. So a newly born pulsar should be spinning at a dizzying speed, right? Like multiple times a second.
Oh, absolutely. A typical pulsar rotates anywhere from once every few seconds to hundreds of times a second. Yeah, the Crab pulsar, for example, rotates about 30 times a second.
But the signals we are picking up from these long-period transients, they repeat every 20 minutes. If the light pulse is directly tied to the spin of the star, that means the star is taking 20 full minutes to complete a single rotation.
Yes. And you have isolated the exact flaw in the assumption right there. The math simply does not support it.
Because it's too slow.
It's not just that 20 minutes is unusually slow, it's that a 20-minute rotation completely breaks the fundamental physics of how a pulsar operates.
Wait, really? Why does the speed of the spin dictate whether the light turns on or off? Shouldn't a slow lighthouse still sweep a beam?
In a mechanical lighthouse on Earth, yes. You just turn the motor down. But a pulsar isn't mechanical, it's an electromagnetic engine.
Okay.
The radio emission is entirely powered by the rotational kinetic energy of the star itself. As the neutron star spins, its massive magnetic field spins with it, and that generates a staggering electric field that literally rips charged particles right off the surface of the star.
Whoa, it pulls its own surface off.
Yeah, and then flings them out into space.
Yeah.
But this entire mechanism requires an incredibly fast spin to generate enough voltage to do that.
So there is a threshold, like you have to be spinning at least X speed to power the beam.
Exactly. We call it the death line.
The death line. Sounds ominous.
It is for the pulsar. As a pulsar ages over millions of years, it gradually loses energy and its rotation slows down. As it slows, the electric voltage drops.
Man.
Once the rotation drops below that critical speed, usually around a few seconds per rotation, the voltage is no longer strong enough to pull particles off the surface.
So the engine just cuts out?
The acceleration stops, the radio beams completely shut off, the engine dies. A solitary neutron star rotating once every 20 minutes should be well past the death line.
Wow.
It should be dead, cold, and entirely silent in the radio spectrum.
Okay, so we were basically looking at an old, rusted, slow-moving bicycle, but it was somehow producing the roaring, deafening engine sound of a Formula One race car.
That is an incredibly apt analogy.
Yes.
We were observing these massive, energetic radio waves that our established, universally accepted understanding of physics says absolutely cannot exist if the source is just a solitary, slowing neutron star.
But the telescope data isn't lying, right? Like, the burst is real.
The burst is very real.
So if the bicycle cannot possibly make the roaring engine sound on its own, I mean, it just physically can't, it means the bicycle isn't alone. Someone else has to be driving right alongside it with a sports car engine.
Bingo. That exact realization is what forced the entire astronomical community to rethink the paradigm. If a single solitary dead star could possibly be responsible for these massive slow bursts, we had to be looking at a completely different kind of cosmic machinery.
And that paradigm shift is what brings us to the monumental discovery of this system, right? ESCAP J1745.
Yes, exactly.
Let's talk about ASCAP for a second, because this is the observatory that finally caught one of these things in the act.
It is. So ESCAP stands for the Australian Square Kilometre Array Pathfinder.
That's a mouthful.
It is. It's an array of 36 radio dish antennas spread out across the remote outback of Western Australia. And it's operated by CSIRO, which is the National Science Agency there.
Okay, 36 dishes.
Right. Instead of one massive monolithic dish, these 36 dishes work together as a single incredibly sensitive instrument through a process called interferometry.
So they link them all up.
Yes. It essentially allows astronomers to survey huge swaths of the sky with incredible speed and detail.
And they use this to spot a brand new long-period radio transient.
They did. But you know what makes ASCAP J1745 the true turning point in this entire field of study isn't just that they found another ticking radio source.
Right.
It's what the astronomers did immediately after they found it. For the very first time, they managed to coordinate a massive multi-wavelength observation campaign.
Multi-wavelength meaning they didn't just use radio.
Exactly. They didn't just listen to the radio waves. They managed to look at the system using X-ray telescopes and optical telescopes simultaneously.
Which, just from a logistical standpoint, has to be a monumental headache. I mean, you can't just walk outside your house with 3 different sets of binoculars.
Oh, it is a phenomenal feat of coordination.
Yeah.
I mean, think about what is required here. You have the radio array tracking the target from the ground in Australia.
Okay.
To get optical, visible light data, you need to coordinate with massive ground-based observatories, perhaps in Chile or Hawaii, and literally pray that the weather holds and that the target is above the horizon during their specific night.
Oh man, the weather. I didn't even think about that.
It ruins observations all the time. And for X-rays, Our atmosphere entirely absorbs X-rays from space.
Which is great for human health.
Very great for us.
So there.
But it's terrible for astronomy. So to observe X-rays, you have to secure observation time on billion-dollar space satellites orbiting the Earth.
So you have to book satellite time, too.
Yeah, and getting all of these distinct, highly demanded instruments to point at the exact same microscopic coordinate in the sky at the exact same minute requires years of proposals and just a staggering amount of luck.
But they pulled it off. They stared at the smog with every type of lens humanity has built. And what did they actually see?
They saw the complete picture. ASCAP J1745 wasn't just emitting radio bursts. It was emitting both radio and X-ray bursts.
At the same time.
Yes. And crucially, those bursts were repeating in absolute perfect synchronization with the orbital motion of the system.
So they didn't just find a suspect. They caught it on multiple cameras from different angles, all time-stamped.
Exactly. If we connect this to the bigger picture, the researchers themselves refer to this multi-wavelength detection as the Rosetta Stone.
Like the actual historical artifact from Egypt.
Exactly that. For centuries, historians were completely paralyzed by ancient Egyptian hieroglyphs.
Right. They couldn't read them at all.
They were looking at these beautiful, intricate symbols, but they had absolutely no underlying framework to understand what they meant. It was just visual noise.
Until the stone.
Right, because the Rosetta Stone featured the exact same decree written in 3 distinct scripts: Ancient Greek, which scholars could fluently read, Demotic, and Egyptian hieroglyphs.
So they just lined them up.
Because the underlying message was identical across all 3, they could finally use the Greek to crack the code of the hieroglyphs.
Okay, so in this cosmic scenario, the 3 scripts are the radio waves, the X-rays, and the optical visible light.
Exactly.
For 30 years, these long-period transients have been speaking exclusively in radio waves, a language that made absolutely no physical sense to us because the solitary pulsar math didn't work.
Right, it was just noise we couldn't decipher.
But now, because ASCAP J1745 is speaking in all 3 wavelengths simultaneously, we can use the X-ray and optical data to translate the radio signal.
You've got it perfectly. And that translation allowed them to definitively identify the engine.
And the engine is?
ASCAP J1745 is not a solitary pulsar. It is a cataclysmic variable, specifically an accreting white dwarf binary system.
Okay, here's where it gets really interesting. We have unmasked the suspect. We know the engine is an accreting white dwarf binary. But what does that actually mean? Let's dissect the physical anatomy of the system because reading about it is just wild.
It really is. So we have to look at the 2 distinct stars involved in this binary dance. Player 1 is the white dwarf.
Okay.
Now, earlier, we discussed neutron stars, which are born from the explosive death of massive stars. A white dwarf is also a dead star, but it comes from a much more common origin.
Like our sun.
Exactly like our sun. When a lower mass star reaches the end of its life, it doesn't explode in a violent supernova. It gently puffs off its outer layers over time, leaving behind this dense, intensely hot, slowly cooling core.
And that core is the white dwarf.
Yes.
So it's dense, but not, a teaspoon weighing a mountain dense like the neutron star.
Right. It's not quite that extreme. It has roughly the mass of our sun, but it's squeezed down into a sphere about the size of the Earth.
Okay, so still incredibly dense.
Oh, the gravity is immense, yes.
Yeah.
But it isn't governed by the extreme quantum weirdness of a neutron star. Now, player 2 in this system is a low-mass red dwarf star.
A red dwarf. So this one isn't dead.
No, this is a living star.
Okay.
It is actively fusing hydrogen, but it is much smaller, cooler, and dimmer than our sun.
So we have a dead, cooling, Earth-sized core and a living small red star. And the key word here is binary. They are orbiting each other.
Orbiting incredibly closely. So closely, in fact, that they cross a critical gravitational threshold known as the Roche lobe.
The Roche lobe. Okay, what happens when they cross that threshold?
Well, it initiates a process of intense stellar theft.
Stellar theft. I love that.
It's the most accurate term. Gravity is essentially a battle of mass and distance. Because these 2 stars are orbiting in such tight proximity, the gravitational pull of the ultra-dense white dwarf on the side of the red dwarf facing it becomes stronger than the red dwarf's own ability to hold on to its gas.
Oh, wow. So it's literally overpowering the other star's gravity?
Completely. The white dwarf's gravity physically breaches the red dwarf's atmosphere and begins to siphon the outer layers of hydrogen plasma right off the living star.
Just ripping it away.
Yes. This process of drawing in material is what we call accretion.
It's a literal cosmic vampire. You have this undead, cooling stellar corpse constantly feeding off the atmosphere of its smaller living companion just to generate these massive bursts of energy.
A vampire's a great analogy.
And it's not a gentle process, is it? Like, it's not just politely sipping the plasma.
Oh, no, it is breathtakingly violent. As the plasma is ripped away from the red dwarf, it doesn't just fall straight down onto the white dwarf like rain.
Why not?
Because both stars are orbiting each other, right? So the stolen material has angular momentum. It's moving sideways as it falls.
Oh, right. It's spinning.
Exactly. So it spirals inward, forming this massive, swirling, flattened funnel of gas known as an accretion disk around the equator of the white dwarf.
Like the rings of Saturn, but made of superheated plasma.
Yes, and moving way, way faster. The material in this disk is orbiting at immense speeds, constantly rubbing against itself, which creates staggering amounts of friction and kinetic energy.
Man, this entirely redefines the math. We aren't looking at a single neutron star just spinning in isolation and running out of juice. The energy powering these long-period transients is coming from the active, violent collision of material being passed from one star to another.
Exactly. The engine is the interaction, not just the rotation.
But wait, if the white dwarf is constantly feeding like this, is it eventually going to devour the red dwarf entirely? How long can a vampiric dance like this actually last?
It is an incredibly long, drawn-out process. These cataclysmic variable systems can persist for millions, sometimes billions of years.
Billions, just slowly eating it.
Yep, it is a very slow, steady drain. As the red dwarf loses mass, the entire orbital dynamic of the two stars actually shifts to compensate.
They adjust their orbit.
Basically, yes. They move slightly further apart or closer together depending on the mass transfer. But over the timescales that humanity operates on, it acts as a remarkably stable, relentless feeding engine.
Okay, so we have the mechanism, the steady flow of stolen plasma. But how does this meal of red dwarf gas actually produce the specific, perfectly timed flashes of X-ray and radio light that we detect? Because friction makes heat, but does it make radio waves?
Great question. Let's start with the X-rays, because the physics there are directly tied to the friction we just discussed.
Okay, lay it on me.
As the stolen material spirals deeper and deeper into the accretion disk, getting closer and closer to the surface of the white dwarf, the gravitational pull gets stronger, and the speed of the plasma increases.
Right.
All that internal friction heats the gas to extreme temperatures. We're talking millions of degrees.
Millions of degrees, just from gas rubbing against gas.
Yes. The kinetic energy is just enormous. And when gas gets that extraordinarily hot, it radiates high-energy light.
So that's the X-rays.
Exactly. The kinetic energy of the falling plasma is converted into thermal energy. The inner edges of that accretion disk and the actual point where the material finally slams onto the surface of the white dwarf.
The impact zone.
Right. That zone becomes so superheated that it glows brilliantly in the X-ray spectrum. The X-rays are essentially the thermal signature of the destruction.
Okay, the X-rays make perfect sense to me. It's the heat of the friction. But what about the radio waves? Because we established earlier that a slow-spinning dead star shouldn't be making radio bursts.
Right, and this is where the true brilliance of the binary discovery comes into play. The radio light isn't caused by the thermal heat of the gas at all.
It's not.
No. It is caused by the interaction between highly energetic charged particles and intensely strong magnetic fields.
Okay, so we're back to magnets. Both of these stars are highly magnetic, yes.
Profoundly magnetic. A white dwarf can have a magnetic field thousands, sometimes millions of times stronger than an MRI machine in a hospital on Earth.
Millions of times stronger than an MRI. And MRIs can rip chairs across a room.
Exactly. It's a field strength we literally cannot fathom. And the red dwarf is also magnetically active, churning out his own complex magnetic field lines.
Okay, so instead of the clunky idea of, like, sparks flying off silverware while eating, which is what I was picturing earlier, let me try a completely different analogy here.
Go for it.
It sounds more like a massive cosmic hydroelectric dam.
Ooh, I like where this is going.
Right, so the physical water crashing down the spillway, the sheer gravity and friction of the plasma falling, that's your heat, your X-rays.
Yes.
But inside the dam, you have these invisible magnetic turbines spinning. The flow of the water forces them to interact, and that invisible magnetic tension is what actually generates the electricity, or in this case, flings the radio waves out across the galaxy.
That is a significantly better and much more physically accurate visualization. I might steal that. The kinetic flow of the plasma is interacting with the invisible magnetic architecture of the system.
There's a term for that, right?
Yes. In astrophysics, this specific mechanism of generating radio waves is called synchrotron radiation.
synchrotron radiation. How does that work in this? And because this whole system is locked in a strict binary orbit, the geometry of how those magnetic fields align and how the plasma flows repeats itself perfectly every single time the stars complete a revolution.
Precisely. As the stars swing around their common center of gravity, our viewing angle from Earth changes.
Right.
The magnetic fields align, the plasma gets accelerated, the synchrotron radiation blasts outward, and Earth's telescopes pick up a massive, booming radio pulse.
And then 20 minutes later?
The stars complete another orbit, the geometry realigns, and boom, another pulse.
That is incredible.
It is a perfectly timed, incredibly complex machine powered entirely by gravity and magnetism.
Which completely solves the mystery. It isn't a single impossibly slow pulsar just breaking the laws of physics. It is a dynamic, interacting binary system functioning exactly as the laws of physics dictate.
It's all just physics doing what physics does.
So what does this all mean for the broader world of astronomy? Why is ESCAP J1745 such a landmark moment beyond just, solving a really cool puzzle?
Well, it changes the future of how we study the galaxy because it gives us an unparalleled baseline. We now know for a fact that an accreting white dwarf binary can produce these long-period, 20-minute radio transients.
The Rosetta Stone is fully translated.
Exactly. Because we have this complete picture spanning radio, optical, and X-ray data for ESCAP J1745, astronomers can now look back at the archives.
Look at the other 11 sources.
Right. They can look at all the other mysterious, isolated radio transients that are hiding deep behind the galactic dust, the ones where we only have the radio horn and absolutely no X-ray or optical data to back it up.
So they can essentially reverse engineer the suspect.
They can definitively say, look, we can't see the X-rays because the interstellar smog is too thick. But because the periodicity, the polarization, and the exact shape of these radio waves look exactly like our baseline ESCAP system, we can infer that we are looking at another cosmic vampire system.
That is such a powerful tool.
It is a vital diagnostic tool for exploring the hidden, dust-obscured regions of the Milky Way.
But this isn't just about cataloging stars, right? There's a broader application for physics itself here.
Oh, definitely. This raises an important point about the nature of astrophysics in general. Exploring these mechanisms essentially turns deep space into a pristine, extreme physics laboratory.
How so?
Well, on Earth, we are profoundly limited by our environment and our technology.
Right. We can only build things so big.
Exactly.
Yeah.
We've spent billions of dollars building massive facilities like the Large Hadron Collider at CERN just to smash tiny particles together.
What?
Or we build massive fusion tokamaks trying to contain superheated plasma with artificial magnetic fields.
Which is incredibly hard to do, apparently.
It's tremendously difficult. And those earthly experiments are incredible, don't get me wrong, but they are limited. We cannot recreate the sheer scale, the density, or the magnetic field strength of a white dwarf star in a laboratory in Switzerland.
No, definitely not.
But the universe has already built these ultimate laboratories out in the cosmos for us. We have white dwarfs acting as natural sustained particle accelerators, generating forces and plasma flows we can barely even comprehend.
And they've been running for millions of years.
The experiment has been running flawlessly for millions of years. We just needed to develop the instruments to record the data and the context to actually read the dials on the machinery.
So we're just watching the results of an experiment we didn't have to build.
Exactly. By observing how synchrotron radiation behaves when plasma is subjected to magnetic fields thousands of times stronger than our best technology, we might unlock fundamental secrets about electromagnetism and fluid dynamics that apply far beyond just looking at stars.
Like things we could use here on Earth.
Potentially, yes. The knowledge gained from observing extreme space phenomena frequently filters down to influence plasma physics, quantum mechanics, and our fundamental understanding of how energy and matter interact.
Wow.
This single discovery bridges observational astronomy and theoretical physics in a really profound way.
It is a massive triumph of observation, global coordination, and just sheer scientific patience. Let's take a breath and recap this incredible journey we've been on today.
Sure.
We started by staring into the impenetrable, dusty smog of the center of the Milky Way, just listening to these impossibly slow, rhythmic flashes of radio light.
The car horn in the smog.
The car horn. And we hit a massive theoretical wall when our established physics proved that a solitary, dying neutron star couldn't possibly be spinning that slowly and still producing radio waves. The engine should have been dead.
Stone dead.
But instead of throwing out the data, astronomers marshaled telescopes across the globe and in orbit, peered through different wavelengths of light simultaneously, and finally unmasked the true engine. We aren't looking at a lonely dying star.
Not at all.
We are looking at a vampiric white dwarf locked in a violent magnetic dance with a living companion, constantly siphoning off its atmosphere to power a massive, synchronized cosmic generator.
It serves as a stark reminder that the universe is rarely as simple as a solitary object acting in total isolation.
It's all connected.
The cosmos is incredibly dynamic, deeply interactive, and it constantly requires us to adapt, discard old assumptions, and build completely new frameworks when the evidence demands it.
It truly does. And as we wrap up this journey, I want to leave you with a final, lingering thought to ponder long after the audio stops today. Think about the sheer scale of the time frame here. These massive, energetic signals were flashing in the dark for 30 years before humanity finally gathered the right combination of tools to understand them.
30 years of just listening to the metronome.
Exactly. If it took coordinating billion-dollar radio arrays on Earth with X-ray satellites in orbit, just to realize that a violent stellar feeding frenzy was happening right in our own galactic neighborhood, what other invisible extreme forces are silently shaping the universe right now?
Oh, there's so much we don't know.
What other massive engines are ticking away in the dark, passing right through us, just waiting for us to develop the correct lens to finally see them? Maybe the next time you look up at the darkest, dust-choked parts of the night sky, you won't just see an empty void. You'll wonder what invisible giants are dancing right behind the veil.